Okay, this is an example calculation for the photoelectric effect. A metal has a wave function of 5 electron volts. What is the minimum wavelength that can be used to eject electrons from the metal? So I'm going to take that 5 electron volts, I'm going to turn it into joules. I'm going to use those joules to predict a frequency for the light. And then with the frequency of the light, I'm going to take that last step and I'm going to move over to a wavelength using the universal wave equation. Okay, so 5 electron volts. Getting rid of electron volts, going to joules. 1 electron volt is 1.6 times 10 to the negative 19 joules. So I got 8 times 10 to the negative 19 joules. And with that in hand, that's my energy that I require. So the minimum packet size, or the minimum photon size that will be able to release that amount of energy, I can find its frequency using Planck's equation here. 8 times 10 to the negative 19 joules, and Planck's constant 6.63 times 10 to the negative 34 joule seconds, and then the frequency. And I'm getting 1.21 times 10 to the 15 hertz. And now I can use the universal wave equation, V equals f lambda, because I know the speed of light, to determine what the wavelength of that light would be. So 3.0 times 10 to the 8 meters per second. Frequency is 1.21 times 10 to the 15 hertz. It's wavelength. And I got a wavelength of 2.48 times 10 to the negative 7 meters, or 248 nanometers. So any wavelength longer than that wouldn't, and once you hit that UV wavelength there, you would see the electrons starting to be ejected from the thing, and as a result you'd see a current.